In the last video, we introduced the concept of multiple cash flows and extended that idea towards valuing ordinary annuities. Here, we're going to work with some other special types of annuities. We're going to work with annuity dues, which are annuities in which the first cash flow occurs immediately. As you can see on the timeline, the first cash flow for the annuity due happens at time 0. That's today. Then we're going to work with deferred annuities, which are annuities in which the first cash flow is deferred beyond one period from today. So this first payment could happen 2 years from now, or 10 years from now, or 100 years from now. And lastly, we'll work with perpetuities, which is an annuity which has no end. It makes payments perpetually. We'll start with annuity due. As I said, for this type of annuity, the first cash flow happens immediately. The key words to know that you're dealing with annuity due are words that signal that the cash flow occurs without delay. Words like immediate, the first payment happens today, or payments occur at the beginning of each period. We can begin with this example. Consider a series of 3 cash flows of $4,000 each with a discount rate of 6% and the first cash flow occurring today. We want to know either the present value or future value of this annuity. Putting it on a timeline, it's going to look like this. Since the first cash flow occurs today, we could put the initial $4,000 payment at time 0. And the next payment would occur at the beginning of the following year, and the next one at the beginning of that year as well. So what makes this any different from the ordinary annuities we looked at previously? The difference comes down to the interest effects of the first cash flow. Let's take a look at how many times interest is compounded on the first cash flow for an annuity due. Interest on the first cash flow is compounded over 3 periods, from time 0 to time 1, from time 1 to time 2, and from time 2 to time 3. And the first cash flow on an annuity due, on the other hand, or the first cash flow on an ordinary annuity, on the other hand, only gets interest twice, from time 1 to time 2, and time 2 to time 3. The result of all this is the annuity due is a larger value. If we look at the formulas here for both present and future value for annuity due, we can see that we simply adjust the ordinary annuity value by compounding one more period. That is, we multiply the ordinary annuity value by 1 plus the interest rate. We can adjust for this very easily in both the calculator and Excel. In the calculator, our inputs are going to be exactly the same as if we're working with an ordinary annuity. N still represents the number of payments. In PMT, payment still represents the payment size. The only change we need to make is we need to tell the calculator that the timing of the cash flows is different. We need to tell it that the cash flows occur at the beginning of each period. So we enter the inputs as normal inputs, but at the bottom of the TVM solver is a slider that has you choose either end or begin. The default is end, but for an annuity due, we need to change that to begin. So press enter on that to change the setting. Then solve for future value as usual. We get $13,498 as the future value. I think it's good practice to switch the calculator back to end mode after you complete the problem because annuity dues are not the standard both in this class and in the financial world. They're a very special case. So let's go ahead and solve this in Excel too. Just as in the calculator, everything remains pretty much the same. We need to make one tiny modification to one of our function inputs. For type, we're going to switch from the default of 0 to 1. By doing this, we're telling Excel that this is an annuity due and that the cash flows are going to occur at the beginning of each period. We can apply the concept of an annuity due to illustrate the importance of starting early in your retirement savings. We have 2 people here, Tim and Mary, who both got their first paychecks and are ready to begin saving for retirement. Tim starts saving immediately, putting $1,500 a month into a 10% APR account today. Mary, on the other hand, she wants to enjoy her first paycheck a little bit, so she delays and waits until the end of the month to make her first deposit. What impact will this have on the retirement amounts that they have in their accounts after 40 years? Well, let's work out Tim's situation first. His situation can be valued using an annuity due since his first deposit will occur today. And we're trying to find the future value. How much will he have in the account in the future? N is going to be 480 months. That's 40 years times 12 months a year. So 480 monthly deposits. We need a corresponding monthly interest rate. So we'll take that 10% APR and divide it by 12, giving us 0.833% per month. The PV is going to be 0 because all the cash flows in this scenario are going to be represented by the payment, which is going to be $1,500. And we'll make it negative because Tim is depositing the money, so it's a cash outflow. Finally, we need to change the settings from end to begin to reflect that this is an annuity due. Solving for FE, we get $9,565,000. That's how much he's going to have in the account at retirement. Now we'll do the same for Mary, who, remember, delayed just a little bit. The setup is exactly the same as Tim's, except we need to keep our cash flow timing setting at the default end of period setting. Solving for Mary's future value, we get $9,486,000, almost $100,000 less than Tim. Now notice that the only difference between them was the 1 month delay in getting started. Everything else was identical, so that little delay magnifies into a significant difference in the end. The next type of special annuity I want to go over is called a deferred annuity. The name kind of gives away what's going on with it. With a deferred annuity, we defer the first cash flow beyond 1 period from today. The first cash flow doesn't happen now, it doesn't happen 1 period from now, but any time further into the future. Because of this, every problem is unique. Some will start in year 10, while others start in year 20. To value a deferred annuity, you can use a 2-step process. The first step is to identify the value of an ordinary annuity. If you look at this timeline, we should be able to make it look like an ordinary annuity, which is something that we should already be comfortable valuing. If I block out the front part of the timeline and imagine the 1 being a 0, then this looks just like an ordinary annuity. And we know how to find the value of an ordinary annuity at time 1. The next step is to discount that ordinary annuity back to time 0. Remember, our goal is not to value the deferred annuity at time 1. Our ultimate goal is to find out the value today, at time 0. So discounting back 1 period to time 0 gives us the value of the deferred annuity today, which is what we want. Let's do another example related to retirement planning. Assume that you'll need $5,000 per month when you retire 40 years from now, and you expect that you'll need 30 years worth of cash flows when you retire. With an interest rate of 3% per year, how much would you need to deposit today to reach your goal? So I have my timeline here, and nothing is happening for 40 years. That's 480 months of nothing happening. But then starting in month 481, I need to make my first $5,000 withdrawal, and then another 359 withdrawals after that. That's a total of 360 total withdrawals, or 30 years worth. If I block out the front part of the timeline, it starts to look like something familiar, an ordinary annuity. And I can find the value of that ordinary annuity at month 480. The N will be 360 monthly payments. I will be 0.25% per month. The payment is $5,000, and we're solving for the present value. How much do we need to put into the account today to make the $5,000 payment happen? Just as a reminder, the settings on Excel and the calculator need to be the default end of period settings, since this is an ordinary annuity. Solving for PV, I get $1,185,000. That's the value of the ordinary annuity at month 480. That's just step 1. That's not what we ultimately want to know. The final step is to discount that value from month 480 back to the present at time 0. Now this is just a basic future value problem. We'll let the $1,185,000 we just found be the future value and discount it back 480 months. Payment will be 0 here since we're just focusing on this one single value. Solving for present value, I get $357,000. I would need to deposit that much into the account today in order to be set up to get the $5,000 a month in retirement like I planned. We can examine this as a more realistic scenario. It's unlikely you'd want to know how much you need to deposit all at once in order to meet your retirement goals. Instead, you'd probably contribute something monthly into a retirement account. So let's analyze that question. How much would we need to deposit each month to meet the retirement goal? Well, we already found that we need $1,185,000 in the account at the retirement date on month 480. So this question boils down to how much do we need to deposit each month between now and the retirement date in order to have $1,185,000 in the account at month 480. This turns out to be just an ordinary annuity problem. I'll be making deposits for the next 480 months, or 40 years, So that's going to be my N. And I want to have $1,185,000 in the future. So that's my future value. And I need to solve for payment. Solving for payment, I get $1,280 per month. That means if I deposit $1,280 per month into the account, I'll have the $1,185,000 at the retirement date that I need, and I'll be able to withdraw $5,000 a month from it. The situation would look like this chart here. We spend 40 years building up the account balance with our deposits, and then once we retire, we draw it down with our withdrawals. The final type of special annuity we'll cover here is called a perpetuity. The defining feature of a perpetuity is that the cash flows continue forever. You get a payment next year, the year after that, 1,000 years from now, 10,000 years from now. They never stop. We can find the present value of a perpetuity with a very simple formula. We could say that the present value equals the perpetual payment amount divided by the interest rate. How does such a complicated idea have such a simple formula? Well, it's derived from the formula for a present value of an ordinary annuity. Which variable in this formula over here is affected by the payments forever aspect of the perpetuity? Well, that's going to be N. And if N is the total number of payments, then N will equal infinity for a perpetuity. If you're interested, try this out. Try to imagine N getting bigger and bigger and bigger. You'll see that the ordinary annuity formula will turn into the simple perpetuity formula. A lot of people get confused by the idea of a perpetuity having a single finite value, but it makes sense when you examine what's really going on behind the scenes. If we expand the perpetuity formula, it looks like this. Just an infinite series of present value calculations. The interesting thing is, the cash flows that occur very, very far into the future contribute relatively nothing to the present value. Say I promise to give you $10,000 a year forever. How much will my payment to you 10,000 years from now be worth? Well, it'd effectively be worth nothing. The present value of that cash flow would be 0 point and then 18 zeros followed by a 6. A very teeny tiny number. So let's do a real life application of a perpetuity. Let's say you want to create an endowed scholarship at the university. This scholarship will give a new student each year $5,000 towards tuition, and the scholarship will continue paying out forever. If the interest rate is 5% per year, how much will you have to donate to make that scholarship happen? Well, applying the perpetuity formula, we set payment equal to $5,000 and divide it by 0.05, the interest rate. And we get $100,000. If you donate $100,000 today, you'll be able to provide a $5,000 scholarship to students at the school forever. I think that's pretty cool. Well, that wraps up the different types of special annuities. And it wraps up our section on the time value of money. But this topic will continue to pop up all throughout the semester in bond valuation, stock valuation, project valuation. It's one of the foundational components of finance, so it's really important that you have a solid grasp on it.